Next, let's see the Schofield transition in liquid helium-3. Since the helium-3 atom is fermion, it was assumed that the Bose-Einstein condensation for the bosons would not cause the liquid helium-3 to become superfluid like it did for the liquid helium-4. However, Oserov et al. Discovered that at the 3 millikelvin, helium-3 transformed into superfluid. The fermion helium-3 atoms form Cooper pairs just like the electron Cooper pairs in the low temperature superconductor, which is how the superfluidity of liquid helium-3 was explained. Since the Cooper pairs in the superfluid helium-3 are p-wave pairs, they exhibit magnetic anisotropy. When there is no magnetic field present, the helium-3A and helium-3B phases appear in two distinct superfluid states depending on the temperature and pressure. So you have helium-3A and helium-3B superfluid states. In this instance, there is a multiple point where helium-3 phase, helium-3B phase, A phase, and B phase, and the normal fluid exist at this multiple point exists. On the other hand, the multiple point disappears when the magnetic field is applied, and this figure, extending the range of helium-3A phase to zero pressure, so TF. In this case, new helium-3A1 phase also appears. So this one. As the applied magnetic field increases, this helium-3A1 phase's range increases as well. The transition from the normal fluid to helium-3A phase, so here in this way, or from normal fluid to the helium-3A1 phase, this direction, from helium-3A1 phase to helium-3A phase, this direction, and the magnetic field is a second order phase transition. The phase transition from helium-3A phase to helium-3B phase, this direction, on the other hand, is the first order phase transition that necessitates the latent heat. Due to its magnetic properties, the helium-3 liquid exhibits a variety of superfluid phases. The superfluid phases in the absence of an applied field are depicted in the left figure, this figure. On the other hand, the right picture depicts possible superfluid states in the applied magnetic field. The two-fluid model also explains the temperature dependence of the superfluid density of liquid helium-3. However, due to the superfluid helium-3's magnetic anisotropy, the superfluid density's temperature dependence differs according to the direction of the applied magnetic field. So, different direction field, we have different sulfuric density data. The figure shows how the polarized field directions affects the sulfuric density of the helium-3A phase as function of temperature. This figure's sulfuric density was obtained from torsional oscillator experiments. The sulfuride transition temperature of the confined liquid helium-3 reduces as the confinement size decreases, much like in the confined liquid helium-4. So in this direction. The figure demonstrates this pattern. In these experiments, the aerosol's tangled pores were used to confine the liquid helium-3. The aerosol is 98.2% porous, with pore diameters ranging from 30 to 80 angstrom. The pressure controls the liquid helium-3 film's thickness. The pressure in the figure has changed by this direction, increasing bars from left to right. So thickness of film is thinnest here, and it is the thickest here. As can be seen, the sulfuric transition temperature lowers as the confinement size reduces. So in this direction, film thickness is decreasing. So sulfuric transition temperature is also decreasing, which is the same behavior as the liquid helium-4. The data on the sulfuric density of bulk helium-3, this one, at pressure of these bars are shown in the inset here. The sulfuric density of liquid helium-3 confined within aerosol is depicted in this figure as function of pressure, film thickness. So pressure is increasing in this direction, and the film thickness is decreasing in the other direction. Okay. As film thickness reduces this direction, the sulfuric transition temperature, this temperature, is decreasing as well. Now let's see the phase transition in helium-3, helium-4 mixture. The helium-3 and helium-4 liquid mixture confined in the porous aerosol behaves differently than the mixture in bulk. The figure shows the mixture's phase diagram. The phase diagram of the bulk mixture can be seen in this figure by a dashed line. So this dashed line is the phase diagram for the bulk mixture. You can see that the mixture's coexistence line, this line, splits off from the sulfuric transition line. So you can see this data, and yes, here it splits off from this triple point. Below point A72 Kelvin, phase separation takes place in the bulk mixture. However, the phase separation does not occur in the confined mixture below this point. enabling the mixing of helium-3 and helium-4, which is even below this point. Okay. Now let's see the phase transition in solid helium-3. The crystalline structure of solid helium-3 can vary depending on the temperature and pressure. The helium-3 atoms have a dipole moment and a spin quantum number of half. The solid helium-3 is regarded as an ideal system of the quantum spin system since it contains no impurities. Thus, the solid helium-3 can be used in research on the quantum spin system. However, since the solid helium-3 has low thermal conductivity, it is hard to lower its temperature. In addition, there is no theoretical basis for the quantum solid helium-3. However, solid helium-3 Heisenberg magnetic system with an isotropic spin interaction is a fascinating magnetic model system. Only the exchange interaction matters from a thermodynamic view of this solid helium-3. Therefore, using this solid helium-3, research on spontaneous ordering and phase change in response to the magnetic field is underway. Since the ordering can be caused by the dipole-dipole interaction, it was expected that spontaneous ordering in the solid helium-3 would be observed. However, the antiferromagnetic ordering was observed at 0.93 millikelvin, which was 1,000 times higher than expected. Thus, hopping exchange between nearby atoms rather than dipole-dipole interaction may result in nuclear spin ordering in the solid helium-3. The ordering temperature was substantially higher than was expected by dipole-dipole interaction as a result of this. In the solid helium-3, the hopping exchange is a real change in atom position that has not been seen in any other system. Due to its high zero-point energy and weak atomic interactions, the solid helium-3 may be capable of undergoing this hopping exchange. The research has focused heavily on the phase transition of the solid helium-3 caused by external magnetic field. In the figure, one of the example is displayed. In this figure, the magnetic field's effects on the phase transition of the PCC structure at the melting point is depicted. Only below the Neal temperature of 1 millikelvin, this temperature, Kelvin, and the critical field of 0.4 Tesla does the antiferromagnetic state exist. This corresponds to low field region here. So below Neal temperature and below 0.4 Tesla, so in this region, antiferromagnetic state. Compared to the disordered paramagnetic state, this region has lower magnetization. Above the field of 0.4 Tesla, so high field region, and low temperature, so this region. It was noticed that malnutrition increased significantly. So it was noticed that the malnutrition increased significantly more than it did in the paramagnetic state. So in this state, compared with the malnutrition in the paramagnetic state, malnutrition in this high field region is much larger. The malnutrition increased to as much as 3 over 5 of the saturation malnutrition in the 0.4 Tesla field. The ferromagnetic state is therefore thought to be competing with the antiferromagnetic state in this high field. In this high field, ferromagnetic state is competing with the antiferromagnetic state. So in this reason, we have high magnetization and large magnetization. The theoretical model depicted in the figure was suggested as possible explanation for this behavior. Two layers of the upspin are parallel to the two layers of downspin in this model. So two layers upspin and two layers of downspin. NMR and Newton scattering experiments verified this spin structure. This model, so-called U2 or D2 model, so up and down, so up to plane, down to plane. So this model effectively explains the magnetic effect on phase change. Odd number exchanges prefer antiferromagnetic structures in exchange involving in more than 3 atoms. So this reason. So odd number exchange appears here, while even number exchange favor ferromagnetic structure. So in this reason, even number exchange is preferred. We can explain the large magnetization in high field by considering that these two states can mix depending on the magnetic field. Now let's see the superconductor transition. Copper pairing of the conduction electrons causes the electrical resistance to zero in low temperature superconductors. There was the possibility that non-magnetic metals overall low temperature states might be the low temperature superconductivity. Alkaline metals, these elements, precious metals, and platinum are the metals in the periodic table that don't have magnetic properties and don't turn into superconductors. These elements' superconductivity has been studied in detail. In particular, the superconductor transition of the alloy Au10X indium X has been observed in order to study the superconductivity of gold by adjusting the amount of the indium that exhibits superconductivity. So indium becomes superconductivity. So superconductor, but Au we have to investigate. So they discovered that superconductor transition was observed at 33, 11, 0.5 millikelvin respectively, when the gold content was 94, 98%. So gold content increases in this alloy. The semiconductor transition temperature is decreased. Right? So pure gold, on the other hand, did not exhibit superconductor transition below 38 microkelvin. It was thought that very minute 10 to minus 2 amounts of chrome or mangan in pure gold interfered with the transition of the gold metal to a superconductor. In precious metals, the electron-phonon interaction is also weak, and the density of conduction electrons near Fermi level is low. These factors may make it difficult for precious metals to become superconductors. The platinum metals, despite having a high conduction electron density and an active electron-phonon interaction, do not exhibit superconductor transition. The Powell group observed RH's transition to a superconductor around 325 microkelvin. The superconductor transition in various non-magnetic metals is therefore the subject of ongoing research on the basis that it may be a non-magnetic metal's general low temperature state. Let's see the periodic table here. The elements with the yellow coloring, this one, yellow coloring exhibits the superconductor transition at the temperature indicated below the element symbols. For example, niobium superconductor transition is 9.2 Kelvin. The elements with the gray color, this gray color, this one, and here. Gray color show the superconductor transition under high pressure. Magnetic metals are marked by thick red lines. So these magnetic metals. The precious metal, this one, copper, PD, silver, platinum, and gold. Blue colored elements that do not exhibit superconductor transition.